Hi everyone. Today we will be discussing vector calculus. So let's begin. Vector is determined by both magnitude and direction. Let us quickly recall components and length or magnitude of a vector. So if we have a vector with initial point P and terminal point as Q, so this vector having an initial point as P and terminal point as Q will have x component as 6 minus 4 2, y component as minus 1 minus 0 minus 1 and z component as 2 minus 2, that is 0. And this vector will have magnitude as square root 2 square plus minus 1 square plus 0 square, or x component square plus y component square plus z component square, which is root 5. So if we choose initial point as origin and terminal point as x, y, z, then we can determine each point in space by a vector, and this vector is called position vector. Yes, so position vector is a vector with origin as the initial point and coordinates of terminal point as x, y, z. So R vector is represented as or you can write R vector as xi plus yj plus zk, right? And this position vector will have magnitude as x square plus y square plus z square. Okay, any vector A may be written as a product of its length and direction. Let me show what I mean. Can be represented as magnitude of A vector times A vector by again magnitude of A vector, where this is the length of the vector and this is unit vector in direction of A. Okay, so this is unit vector in the direction of A, and okay, again let us quickly recall dot product and cross product. So if we have two vectors A as and B as, So dot product is defined as magnitude A, magnitude B, cos theta, where A1, A2, A3 and B1, B2, B3 are the component of respective vector A and B. Also, you can write dot product of A and B vector as A1, B1 plus A2, B2 plus A3, B3. Cosine may be positive, 0 or negative. Vector A is called orthogonal to vector B if A dot B is equal to 0 or cos theta is equal to 0, where theta will be equal to pi by 2 or 90 degree. Dot product is a scalar. So in connection with rotations, we require a product of two vectors, which is again a vector. So let us study cross product, which is a vector product. So A cross B is defined as magnitude A, magnitude B and sine theta. And of course n vector, such that A vector, B vector and n vector from a right-handed system where n is a unit normal vector perpendicular to plane of A and B. Unit normal vector perpendicular to plane of A and B. Let me show this with a figure. If this is B and this is A, yes, let's say we have this vector perpendicular to both of them. Yes, so unit normal vector n is also in this direction, and this is A cross B vector. Yes. Also, with the help of determinant, you can find A cross B as I, J, K, and writing the component of each vector A1, A2 and A3, B1, B2 and B3. So, okay. So, see here. So, the unit vector perpendicular to two given vectors A and B is given by A cross B by magnitude A and sine theta, or you can write as A cross B by A cross B mod, magnitude of A cross B. Next is gradient of scalar function. So if we have a scalar function as right, so gradient of f will be del f by del x del z by del f del z So gradient is defined as del operator. This reads nebula or del. So which is del by del x plus del by del y plus del by del z. Yes. This rate is defined by the partial derivatives. So we know that r vector, position vector, is xi plus yj plus zk, and magnitude as x square plus y square plus z square, and r square is x square plus y square plus z square. So let us find the gradient of this position vector. So let us differentiate 2r dr by dx is equal to 2x dx by dx. So also 2r dr by dy is equal to 2y dy by dy. Again differentiating z square with respect to z. So 2r dr by dz is equal to 2z dz by dz. So we can rewrite this as dr by dx is equal to x by r, dr by dy is equal to y by r, and dr by dz is equal to z by r. So del r, gradient of r, we get as I del r by del x, which is x by r, plus j del r by del r by del y, which is y by r, plus del r by del z, which is z by r. So again del r is equal to x I plus yj plus k zk whole divided by r, because we can take r out as common. So gradient r is equal to, or del r is equal to r by vector by r. Yes. Again, if we have to find del of log r, so which will be 1 by r del r. So 1 by r, and del r is r vector by r, so r vector by r square. Similarly, if you have to find gradient of 1 by r, so minus 1 by r square del r, which will be minus 1 by r square into r vector by r, so which is minus r by r cube. So again, if you have del r raised to the power n, so n, differentiate r with respect r raised to the power n with respect to r. So n r raised to the power n minus 1 del r. So which is n r n minus 1 r vector by r. So which is n r n minus 1 minus 1, that is n minus 2 r vector. See, these are the important results. Okay, pay attention to these. And yes, using vectors we can find the area of triangle and parallelogram. So area of triangle will be half of A cross B, and area of parallelogram will be, if two vectors are given, so will be area of will be A cross B modulus, where this vector and this vector are adjacent sides. Okay. Okay, if we are given coordinates of this point and this point and this point A, B, C. So this is A vector and this is B vector. So this area of triangle can be found out by this formula. Okay. Vector product is not commutative, that is B cross A is not equal to A cross B. So B cross A will be equal to minus of A cross B, and vector product is not associative even. So A cross B cross C is not equal to A cross B cross C. Let us see a scalar triple product. So scalar triple product, if we have A component as A1, A2, A3 and B vector component as B1, B2, B3 and C component as C1, C2, C3. Scalar triple product is defined as A dot B cross C, or A1, A2. We can express this as the expansion of a third order determinant A1, A2, A3, B1, B2, B3 and C1, C2, C3. Also, we can interpret A dot B cross C scalar triple product as magnitude A B cross C cos, say, beta. So the absolute value of this scalar triple product is actually the volume of the parallelepiped with A, B, C as edge. Okay, volume of parallelepiped. Let me show what I mean. So let's say we have this as B vector, this as A vector and this as C vector. C vector. Then let us draw a parallelepiped. Okay, so with A, B, C as edge vectors, where A cos beta represent the height h. So this is h, right? Is, and this is beta. This is angle beta. So this is similar to the cross product, geometrical interpretation of cross product. Yes, A cross B. So if we draw this as OA and OB, this is vector A, this is vector B, and if this is the height, let us extend this. So where B sin theta is the height of this parallelogram. Okay, so A cross B, B sin theta represent the height of this parallelogram, and A vector, magnitude of A vector is the base of this parallelogram. So we know that area of parallelogram is base into height. So geometrically, absolute value of A cross B represents the area of a parallelogram. So next is directional derivative. Directional derivatives. Directional derivative is the rate at which any function changes at any particular point in a fixed direction. I repeat, the directional derivative is the rate at which function changes at any particular point in a fixed direction. Which is defined as, if we are given f, x, y, z, so directional derivative is defined as gradient f. If it comes negative, the minus sign will indicate that f decreases in the direction of A, right? Let us have an example. So find the directional derivative. Find the directional derivative of the function in the direction of 3i minus 4k at the point 1, minus 1 and 1. So given function is xyz okay. So given function is xyz and vector field is given as 3i minus 4k, which has magnitude, let's say A, so which has magnitude as root under 3 square plus minus of 4 square, which is 25. right? Now the unit vector in the direction of n in the direction of A is 1 by 5 3i minus 4k. Now we have to find the gradient del f in order to find the directional derivative. So del f will be equal to difference, take the partial derivative of x y z with respect to x, which will be yz, and again with respect to y and with respect to z, which is xy k. Now the directional derivative is, so the answer will be 1 by 5 3i minus 4k dot yz I plus xz j plus xy k. So let us put the value of x, y and z, 1, minus 1 and 1 respectively. So we have 3 Okay, let's first take the dot product. So 3 times yz, okay, I dot I is 1 because cos 0 is 1, plus there is no component for j, so 0, plus 4 times xy. Now put the value of xy and z. So 1 by 5 3 into minus 1 into 1, so minus 3 minus of okay, here it is minus, so minus of 4 into x into y, that is 1 into minus 1, again minus 1, so it will be plus. So we have 1 by 5 as the answer. Let's have a second example. So find the directional derivative of function x square minus y square plus 2z square at p 1, 2, 3 in the direction of PQ, where Q is 5, 0, 4. So first you need to find out the PQ vector, which is Q minus P. So 5 minus 1, 4i, 0 minus 2, 2j, 4 minus 3 plus 1k. So now we have PQ vector. So find out the gradient of f. So which is 2xi minus 2yj plus 4zk. Now, so del f at point 1, 2 and 3 will be, put the value of x, y and z. So 2i minus 4j plus 12k. Now we need to find PQ. Okay, so PQ was 4i minus 2j plus k. So 4i minus 2j plus k by root under 4 square 16 plus minus 2 square 4 plus 1 square. So root under 21. 4i minus 2j plus k by root 21. Right? Now find the dot product of this result with gradient of f. So which will be gradient of f is 2i minus 4j plus 12k. So we will have 8 plus 8 plus 12 by root 21 or 28 by root 21 as the answer. Let us see one more example. Find the directional derivative of a surface f x y z square plus x z at 1 1 1 in the direction of normal to surface 3x y square plus y is equal to z at 0 1 1. So here, so let's find A, which is gradient of this vector, gradient of say del, say g. So del g is I 3y square plus j. So if you take z from right hand side to left hand side, okay, so j 6xy plus 1, okay, and plus k, so minus k, okay. So if we put the value, the given point is 0 1 1. So at the value, at the coordinate 0 1 1, we have 3i plus j minus k. So a by a magnitude a is 3i plus j minus k by root under 9 plus 1 plus 1 11. Okay. Now let's find del f xyz square plus xz. So partial derivative with respect to x, we have yz square plus z, and with respect to y we have xz square plus with respect to z 2xyj plus x. So del f at given point 1, 1 and 1 will be equal to 1, 2i plus j plus 3k. So directional derivative is del f dot, right? So we have 6 plus 1 minus 3. 7 minus 3, that is 4 by root under 11. Okay. So if you have to find the angle between two surfaces, so angle between two surfaces is nothing but the angle between normals drawn at their surface. So if f and g are any two surfaces and theta is the angle between them, then cos theta is defined as del gradient f gradient g by modulus gradient f and modulus of gradient g, right? And if the two surfaces cuts each other orthogonally, then del f dot del g is equal to 0. So let us understand this with an example. Find the angle between surfaces x square plus y square plus z square is equal to 9 and x square plus y square minus z is equal to 3 at point coordinates are given as 2, minus 1 and 2. So let us find gradient f. So 2xi plus 2yj plus 2zk, right? So at point 2, minus 1, 2, which will be 4i minus 2j plus 4k. Similarly, del g is 2xi plus 2yj minus k, so which is 4i minus 2j minus k. Clear? So cos theta is gradient f dot gradient g by magnitude of gradient f and magnitude of gradient g, so which is 16 plus 4 and minus 4 by root under 16 plus 4 plus 16, that is 36, and this is 16 plus 4 plus 1 or 21. So answer is, this is reduced to cos inverse 8 by 3 root under 21. Okay. Next is gradient as surface normal vector. Gradient as surface normal vector. So let us understand this with an example. Find a unit normal vector n of the cone of revolution which is given as z square is equal to 4 x square plus y square at point P102. So So let us rewrite the function f as 4x square plus y square minus of z square. Now gradient f is 8xi plus 8yj minus 2zk. At point 102 we have 8i minus 4k. So now see f is a normal vector of the cone at point P. Okay. So unit normal vector at point P will be gradient f by gradient modulus of gradient f. So which is 8 minus 8i minus 4k by root under 16 plus 64. So which is 4 root 5. So answer is 2i minus k. So this is the unit normal vector at point P. Okay. And the other one is minus n, which is 1 by root 5 minus 2i plus k. Yes. So next is divergence and curl of the vector. So divergence v is defined as d v1 dx plus del v2 del y plus del v3 by del z. Okay. So this is called the divergence of v or the divergence of the vector field defined by v. So gradient v, we denote that as, the notation was del v del f. So for divergence we write del dot v. Okay. So if we have to find, let's say if v is equal to 3xz I plus 2xyj minus yz square k, then divergence v will be 3z plus 2x minus 2yz. So see here, divergence v is the scalar, whereas del f was the vector. Okay, so divergence v is scalar, gradient f was vector. Fine. And del dot del v is called the Laplacian of f. Del dot del f or v is called the Laplacian of v. Okay. This can also be written as del square v. So or divergence of gradient v. Yes. So del square f by del x square plus, sorry I have taken v, del square v by del square v by del square y del y square plus del square v by del z square. So this is the Laplacian of v. Next is curl. So if v xyj is given as v1i plus v2j plus v3k, then curl v is defined as as the determinant of ijk del by del x, del by del y, del by del z, and v1, v2, v3, where v1, v2, v3 are the x, y, z component respectively. Yes. Since the curl characterizes the rotation in a field, so if curl v is 0, that means the field is irrotational. Or conservative. Similarly, if a vector v whose divergence v is 0, if divergence v is 0, then such vector is called solenoidal. Right? Now that we have learnt gradient, divergence and curl, so let us derive some important result. Yes, so we want to find divergence of curl of f vector. Okay, so let us say we have f vector as f1i plus f2j plus f3k. Okay, so curl of f is equal to I j k del by del x, del by del y, del by del z, f1, f2 and f3. So let us expand. I del by del y, f3 minus del by del z, f2, minus j del by del x, f3 and minus del by del z, f1, minus del by del z, f1, k plus k del by del x, f2 minus del by del y, f1. Okay. So now divergence of curl f is del by del x, del f3 del y minus del f2 del z plus del by del y, so minus del f3 by del x plus del f1 by del z plus del by del z, del f2 by del x minus del f1 by del y. After simplification, del square f3 by del x del y minus del square f2 by del x del z plus del square f3 by del x del y. Okay, this is minus plus del square f1 by del y del z plus del square f2 by del z del x, okay, minus del square f1 by del square y del y del z. See, this and this got cancelled, this got cancelled, and this got cancelled. So we have 0. So divergence of curl is equal to 0. Okay, or del dot del cross f is equal to 0. Second, let us derive curl of gradient f. Yes, so gradient f is equal to del f by del x I plus del f by del y j plus del f by del z k. Here f field is a scalar field. So now let us take curl of gradient of f I j k. So del by del x, del by del y, del by del z, del f by del x, del f by del y, del f by del z. Let us simplify del square f by del y del z minus del square del y del z minus j del square f by del x del z, okay, and del square f del x del z minus del square f del x del z plus k. So del square f by del x del y minus del square f del x del y. See, this expression reduces to 0. Yes. So 0i plus 0j minus 0j plus 0k, which is 0. So we can write this as curl of gradient f is 0 or del cross del f is equal to 0. So these two are the important results we just obtained. Okay, so you can write this as dc is equal to 0, divergence of curl is 0, and you can remember this as cg is equal to 0, curl of gradient is equal to 0. So let us wind up here. We will meet in the next lecture. We will see line integrals, Green theorems and Stokes theorem in the next lecture. Till then, keep preparing. Thank you.